Good morning. Welcome to the last class, the last big data lecture in the last lecture in big data class. Yes. So today, we have two topics to discuss. They are relatively short. I left them, for the end, just to cover it. First is, covering data issues, possible data issues that can arise when you are collecting a ton of data, something that I think it's pretty useful to people here because it aims to cover, issues that even if you aren't a computer engineer or computer scientist, right, a programmer, developer, it can help you. It's something that you can raise your hand, bring attention to if you are working on a project that involves large data collection. And of course, for the programmers, it's just extra knowledge that you may find useful. After that, we are just going to, have for the final topic a small discussion regarding what topics, some future trends that are currently arising in big data that you may want to pay attention to if you're discussing, big data and what direction it's going in the future. So let's start with these data issues that we want to discuss. Basically, whenever we are collecting data, we want to make sure the data is accurate, is consistent, and reliable, so we can run any analysis that can support our decision making in the future. Of course, when we are collecting, as I said, big data, we have a large volume and a large velocity of the data, a large variety of data. It's much harder to make sure that all the data is fine when you're collecting 100 data points a second versus when you're collecting, I don't know, a couple data points a minute. And even if you have breaks in between data collections, big data is, pretty much continuous. So there are some issues where, you want to, that scaling basically exasperates, increases, and makes it even harder to make sure that everything is fine. What the process? So what if data is wrong? Obviously, you can. First, it's a waste of energy, waste of storage, waste of processing power that you use to do ETL tasks and store it somewhere and so on. Second, if it's inaccurate, it can lead to wrong insights, wrong conclusions, and so on. So, for example, if you have two stores, one store you don't have a proper pipeline of data set up for one store, and you're not getting all the data from it. You may see like, oh, that store isn't making proper sales. There's something wrong. We need to invest money into retraining people there, or promoting it, when in actuality you are just not getting all the data because there was an error down the way. That's a pretty extreme example, but yeah. So here's where we're going to basically discuss a couple of things like data validation, data cleansing, governance, monitoring of data, to just uh, discuss and see whether this is what you can do to address here. I also mentioned here machine learning, as someone who does a lot of machine learning modeling, machine learning processes. Something that I often tell to my partners on a project when we are working is the model can only be as good as the data you feed it. If you have poor data, you're going to get a poor model. There's a term that's often used. It's called trash in, trash out, right? You can't. It's very hard to get a good data, good models from bad data, right? So that's something that we're going to discuss. But when we are examining data quality, there are a couple of different elements that we want to discuss here, that we want to note. So, for example, first is accuracy. That's how well, if that data recommends, how well that data reflects real world values. For example, is if the actual temperature in the room somewhere that I'm monitoring is 25 degrees Celsius. If I have a sensor there that tells me it's 20 degrees Celsius, that's a significant error. So that is the term accuracy that we're referring, the type of accuracy that we're referring to. Completeness is if you're getting all the possible data, right? If you have like if you are measuring again temperature that you in a hotel, you get data for all hotel rooms. Consistency is another problem. As I said before, I used a lot of times example here. If you're having different sales points, like you're selling on Amazon, Alibaba, Etsy, eBay, you'll get the same thing at different sales stores, right? You might be getting a different format inside. You want to make your data consistent so you can analyze it more easily, right? And you don't want to accidentally during that transformation make a mistake, like store, for example, order number in the column where you expect I don't know, the sale price to be at, because that can obviously mess up with your model. Finally, whether it is timely, whether what does this mean? It means whether the data that we are collecting is up to date. If you go to check the data now, you don't want to check necessarily last year's data. You want to check the data up to ideally this moment, right? Right now, because that's what you're interested in. Yes, there are some analyses where you want to look at historical data and so on, but whichever point you want to observe, whether it's a year back, whether it's right now, you want to have data up to that point, not stuck somewhere because you are not processing it properly. And finally, you have data validity, that is essentially whether you have a format standard, you have constraints, you have limits that you set up. Does the data fall into this? Basically, you will use these defined formats standards to assure these other dimensions of data, like is it within a certain accuracy or not, whether it's complete, whether it's consistent. You will check whether data is in the appropriate format. So that's something that you want to check via validity, right? You want to make sure the data is valid, that follows these other elements. I mentioned already certain issues. For example, volume is whether when you're doing quality checks. If you're doing a quality check on a small Excel table, maybe a few hundred students, or for example, when we were checking, when you were applying to this class, we were checking which people applied validly, which people didn't. Some of you typed in a wrong, typed in their email under their last name. Some people didn't type in. There was a few hundred, so we just checked that manually, right? We didn't. But we're talking about big data. We're talking about volumes where you can't check stuff manually because you have millions of data points, right? You can scroll through a table and figure it out. Same goes about velocity. You're loading a lot of data locally. Checking it if you're trying to get some sort of a data streaming, real-time data streaming, that's a possible issue. A variety, as I mentioned, you have a lot of different data sources, data types, how they're formatted, and you need to transform that. And that's something that can introduce an error, right? Because if you're misformatting something, or if you're trying to do OCR on a PDF, you're trying to do OCR on a PDF. In that case, you want to, what happens when your supplier changes the PDF format they use to deliver the data to you. that can cause additional issues. So it doesn't have to be like it can suddenly happen. Errors can suddenly happen here. We also talked about distributed environments. So if we have if we have a data set stored in different areas, that's obviously can lead to a problem, because what happens if one piece of data gets corrupted? It's not corrupted in the other side, and so on. And obviously, you have, as I mentioned, changes can be dynamic. You won't always going to get information up ahead and be told like, oh yeah, we're changing something. Sometimes the format, for example, as I mentioned, the format of the data you're getting in changes because one of the services that you use, for example, for sales, has changed the format they are delivering the bills in, because they decided it looks nicer now, and it breaks the entire system. So what are some steps that you want to do? First is, you want data profiling. We talked about the data collection, practical data collection class. We talked, if you attended, you will remember that we talked about some descriptive statistics and distributions and so on that you can use to determine whether there are anomalies, outliers, and so on in the data, right? Any quality issues. That's something that you can do. That's called data profiling, right? And you can do it at scale if you have powerful enough computers. You can, as you mentioned, you can perform validation, have a list of rows that you check data against to make sure it satisfies the format, to make sure it satisfies the certain range. If you are to know that you aren't getting wrong data. That, for example, if you want to track the sales price of your item, it's not going to be negative. That if you're selling pens, it's not every pen is going to sell for more than $5. That's something that kind of rules can be used for validation. As I mentioned, when you have pipelines, when you have stuff that follows from point A uh, that follows, from point A to point B. This connection here is the pipeline. You can insert different, changes and elements here, so you can clean up the data, especially if you know what kind of errors are happening inside. Metadata management is very important, like so you can analyze and track data quality and make sure what's going on. If you're storing something, when it was collected, when it isn't, and you can immediately store quality measurements, whether something was checked, whether something wasn't checked. And as I mentioned last time, you want to have dashboards that monitor existing systems so they can check whether there are any significant issues with data. If you have a graph somewhere that follows your data values and you suddenly see a spike on it, it probably indicates an error, something that happened because it's not normal compared to other information. Okay, just okay. So I use the term data governance. Data governance simply means establishing policies and standards for the data quality. So at your organization level, or if you work in, for example, healthcare, you might have this data governance done at some higher level, but this is usually done at the level of an organization. You're going to have policies and standards that define what quality data is, right? What falls under high quality data and what doesn't. And you also want to define, roles and responsibilities for maintaining that data quality. Does that fall to people who collect the data? Does that fall to people who enter the data into the system? For example, I worked on a project where we were collecting how to describe it, radio scans of radar scans using a ground penetrating radar to determine whether the what pipes are under the area where you cross. So you can, if you need to dig, you need to replace a pipe or somewhere you don't need to dig out a large area. You can determine exactly where the pipe is, at which depth, and fix it there exactly. So to do this, we had people who were scanning the ground, and we had people who were entering that data into the system. And you need to actually know which of these people are in charge of data quality. The people who are collecting the data, will they, when they get the data of that ground penetrating radar, are they going to immediately be in charge of checking it and submitting it? While they're collecting the data, should they monitor it, see what's going on, or should that fall to like an engineer who is entering the information? So let me just, this is that ground penetrating radar machine. So it has a tablet, it shows what's going on under it. For example, we concluded that, and this is the type of image that you get. We concluded that without these arrows as annotations, we concluded that people should, the people who are actually moving this should be checking to make sure there aren't any massive errors, and the people who are entering into the system should also check it to make sure everything is fine. So double check. For some stuff, like if you're doing healthcare, the doctor has to be in charge. The doctor, when they are collecting the data, if they are performing something like a cystoscopy or something like that, they need to check that data, because once the data comes to me, I'm not a doctor, I can't identify whether something is fine or not fine. And that's essentially what data stewardship is. You assign, people to be stewards of the data, to be in charge of certain data at certain stage, right? Whether once the data is, if we are talking about like a doctor is doing cystoscopy, he is in charge of it until that the data changes form and it's stored in like a NumPy format or something that I'm going to use for model training. Audit trails for the changes and monitoring. So basically you want to track what is happening to the data at each step, what are the changes that are done to the data, so you can more easily identify whether there is any error or something like that. So there are different tools for checking data quality. Here are some, just in case you need to do something in the future, you need to suggest something. Here are some as advices, for example, for checking, data quality, seeing whether large, so we're talking about big data, not just, doing basic statistic analysis on like an Excel data set or something like that. So we have Apache Griffin, Great Expectations is a software, Deque. If we're talking about like ETL platforms that also support that are a bit more detailed when it comes to data checking, as opposed to just running pure, extract, transform, load tasks. You have Talend and Informatica. If you wanted to work on cloud, you have AWS Glue, Databrew, Google Cloud Dataflow, Azure Data Factory. Those are, tools again in the cloud. We talked about the cloud and the benefits of it. For just monitoring, you can use Datadog, you can use Grafana. We also mentioned Prometheus. And of course, so that's very, very popular today. I personally done a lot of this, is using artificial intelligence and machine learning to detect data that isn't fine. This is very good for multivariate data, where you have a lot of variables and you want to determine whether something is fine or not. Profiling data is, essentially, again, we talked about this in practical data collection. If you are a part of that class, you want to understand how the data looks like. And when you're creating a data profile, you're looking at the data that is valid. For example, maybe a subset of data, maybe you get out of 1 million data points that you collect, you get 1,000 data points, you get them checked properly by an expert. And then you analyze it and determine statistics and rules, maybe develop a machine learning model that you will use to check the remaining information. All right. So here is an example. If you have like 20,000 patients, you can't check 20,000 patients manually, but you can extract few hundred patients, send them to different doctors, right, and tell them, okay, check if this data is fine. Once they say like, if data for these few hundred patients is okay, once they confirm it that this data is valid, right, you're going to grab it and you're going to say like, okay, since this data is valid, I'm going to assume most people are going to fall somewhere within these ranges of data. There are going to be significant outliers and so on. Obviously, don't be overzealous with this. You can always accidentally sample a biased set of data and miss something. What enables you to do this is something that's called the law of big numbers, which says that if you have a large data set and you sample a subset of certain size of it, it's going to follow the same statistical distribution and so on. But if you have a very varied data set, you can still introduce a certain bias and discard the data that isn't. So, check it. If every few hundred data points you eliminate a single outlier, that's fine. If you're eliminating, if every second data point is eliminated as an outlier for some reason, that's probably some sort of an error. So, whenever you're doing automated analysis like this, don't go into it blindly. Make a note of like what data you're eliminating or not. What are some, validation checks? First is schema validation. You want to make sure that data adheres to, again, if you're putting it into a table somewhere, it follows, whatever predefined rules exist. You want to check the ranges of data, to make sure that, again, as I said, if you're selling pens, you aren't selling them for negative values, you aren't selling them for hundreds of dollars, very probably. So you're going to check the range. If the someone tells you they sold, like I know you're selling cars, someone tells you they sold the car for $10, they probably hopefully made a mistake right when entering the data inside. Same goes, for validating formats, whether date is probably the worst. You ask, here's 20 of us in the class, if I ask us to enter today's date in chat, everyone is going to enter it differently, right? It's some people are going to use slashes, some people are going to use dots, some people are going to put the month before the date, some people are going to put the year first. Yeah, it's the dates are horrible. Same goes with emails, same goes with names. Some people use Latinic text, some people use Cyrillic text. There's a lot of stuff that can happen doing this. Referential integrity, that's more for, with specifically databases, ensuring that foreign keys and references are okay as you input the data. And again, I mentioned automated testing as a possibility. So what are some things that you need to pay attention to when you're cleaning data, when you're preparing data for further analysis? First is handling missing data. Whether you want to do imputation. Imputation means if you have a table with empty values, you want to enter values in there based on certain statistics or certain analysis. Boltzmann machines exist for imputing data. Or my honestly preferred method, if you have a lot of data, is removing incomplete records. Because again, this inputted data is something that you're already making an assumption, and then you're using that assumption when you're training your model. Yeah, there are possible issues, with this. If you're talking about something where you have like 100 data points and you can sacrifice any data points for analysis, sure. But if you have or you have something like, you can't delete data because, it's, I know, a student data in college, and you need to input certain data to assume like a GPA or something like that, or where they are from, etc. You can just delete the student, right? You want to input that data even if it's wrong for the current analysis, just to cover your bases. You want to standardize what the format is going to be, how you're inputting dates, what units of measurement you're using. You don't want someone to this is something that I actually work with for a store, for a local store here in Croatia, a chain of stores, right? We were analyzing the data. We noticed that some people are entering in decagrams because that's what you commonly, at least in Croatia, if you're, buying like cheese or salami, you're going to use decagrams. You're going to say 20 decagrams or something like that to order, to get your cheese or salami cut to you. But they were expecting the input, when they were ordering. They were expecting their employees to input values in kilograms, and basically what happens is that the some of them checked and so like, oh, this should be kilograms, so they entered it in kilograms, but others spend the whole day talking in one unit and enter, and they would automatically enter it in decagrams, right? So that's sort of a problem where you want to standardize that and you want to check it and we want to make sure, again, if you're per sale, if you're selling 10 kilograms of salami, that's probably false. You're probably selling 10 decagrams, right? Or something like that. You want to make sure that this is fine and use it in checking later. You want to remove duplicates. Duplicates can cause issues when you're creating models later on, and duplicates get generated really easily. Again, if you find an error, either drop the column, either not the column, the row, fix them. If you don't have a lot of errors, you can let them be fixed manually, right? Or have some automatic rule if you have a lot of errors. As I said, you can detect per cell, this person sold ordered 20 kilograms of salami, 20 kilograms of cheese. Well, in reality, they probably ordered 20 decagrams, so we can adjust that error, automatically, and that is something that's done, in transformation pipelines that you can reuse later on. We talked about data monitoring, so I'm not going to, go into details here, but I just want to repeat that if you have like a dashboards or monitoring systems where you can track what's happening to data as you collect it, that's very, very useful, and it can help you a lot in setting up the information properly and figuring out that an error happened as it happens instead of fixing it later. So you want to be proactive, you want to check that as it happens. And the benefit of this is that you can you can monitor data. A single person can monitor data for like 20 different sources automatically if you design a good dashboard. I mentioned distributed systems. We talk about distributed systems and so on. That can be a problem. Why can be a problem? First, you want to use distributed frameworks. You want to use something like Apache Spark or Hadoop or something that allows you to check the data automatically, right? Because don't create your own distributed system by like manually copying stuff and calling that redundancy because you will make mistakes. If you create the data here, you save it there, and then you copy it here manually. What happens is usually you will do some updates here, fix errors. You won't fix errors here. You will that first computer will die. The hard disk will error out or something. You will go collect this data that you stored in backup. You think it's cleaned. It's actually not. You haven't corrected the errors because you haven't done the backup properly. With actual distributed frameworks, that kind of stuff is much less likely to happen because they are designed to automatically take care of that and replicate data changes. So that's and they also have reconciliation jobs built in, so they have tools that if something is wrong, it will get resolved either automatically or with little input from you. Okay, so when we're talking about data lakes, data warehouses, there is a term that is used, which is called data swamp, which is essentially when you have a data lake, but you don't, as I said, data lake, let me remind you, if you don't remember, is when you just have a server somewhere, or a cloud service or whatever, and you're just feeding information into it and storing it. That's an oversimplification. Obviously, you want to store data in some proper way. You want to store metadata with the data that describes at very least what type of data is, what is the source, when it was collected, and so on. If you fail to do that, if you fail to do the proper metadata tagging and so on, you will end up with something that's called a data swamp, which has a ton of information, but you can't actually use it because you didn't identify it properly with any metadata. You just dumped it into place. Think of it, if you ever had to look for an image for a picture that you took and backed up someplace, 5 years back, and now you suddenly you're going through a ton of backups and Oh, hello. I seem to have disconnected for a moment. My apologies. Something was wrong with my internet. I hope you can hear me now. So let me.
Yes, we can hear you.
Okay. Thank you. Yeah. So something with our internet here seems to be problematic. I hope it won't cause us further issues. So let me restart. Basically, with this slide, basically, what are some common issues that you may have with data? That's what we were talking about. First is missing data, as I mentioned it. In an Excel table, you may have values that are unavailable, whether that's null, nan, or something like that. Let me just cover a couple of examples. For example, if you have no data, if it's empty, that's something that we call, no data, lack of data. Null is something that's commonly used to indicate this. Null isn't zero. It means that there is no absolutely no data there. Maybe it wasn't inputted. Maybe we weren't able to input it. But essentially, it's an empty cell that's indicated with a value that's called null. Uh, just so we can usually, why do we insert null instead of just leaving that empty? Because empty cell is ambiguous. Was it an error? Maybe something isn't being displayed properly. Maybe this is a stupid example, maybe, but the text is colored white in an Excel table, and I think it's empty, but it actually has a value there. Uh, it sounds stupid, but it's something that does happen. Having a null as a value is something that I know this wasn't left empty on purpose or some reason like that. It's empty, but it's purposefully empty. I know it wasn't like an error after the data collection happened. Another value, if you're talking about possible values that can be inputted, is nan. Nan simply stands for not a number, right? So this is something that can be, again, there's an error if something, if a process expects a number but you enter text or stuff like that, that can be a nan. Noisy data is, data that has a lot of data points that are mistaken or not relevant. So we have a lot of noise, in it, a lot of data points that don't really make sense. You have a lot of duplicate points. That's something that essentially when you have a duplicate, we're talking about the complete duplicate. So something like if we're entering information and we are all entering our age, of course, we're going to have duplicate values. Of our average age, there will be multiple people here who are, I don't know, 25, for example, or 22. And that's obviously some sort of an information that we can get, right? We can't even create a distribution which can duplicate values, but we're talking about completely and not like accidentally repeated entries, like fully repeated entries, like you're the same person. If I'm asking you, like, write down your age in chat, and you type in your first name, last name, and then your age, and then another person happens with first name, last name, and the same age. There are two possible causes of these. First, duplicates can be because I didn't collect enough variations, enough variables in data. Because, for example, it's realistic that someone can have your first name, your last name, and your age. So if we are going, if we are talking about collecting data on a level of an entire country, there will be possibly a lot of people who will have that overlap, in names, right? In names and age. So I didn't collect enough information. I need additional variables. That's one source of duplicates. The other is just errors. Maybe someone fills out a form twice or hits enter twice, and because something is loading and it enters data twice, that's something that can happen. Inconsistencies, again, different data formats, different units, different values entered. Some people, misunderstand what is the expected data format. So that's why you get today, especially when you're entering a date somewhere, you get like a small calendar to fill out and select your data instead of typing it in manually to make sure everyone follows the same format, right? And again, outliers are any extremely extremely in values that are extremely outside of the expected values. So if you're measuring the height of people and you get like 160 centimeters, 175 centimeters, 180 centimeters, 192 centimeters, values like that, and suddenly you get a measurement that is 5,000 centimeters. That's probably an error, of some sort. Again, I already mentioned this, but let me repeat it. You have what happens when you have a missing data or an erroneous data. You can delete completely that row. You can input data. We will mention it here, but some base methods suggest input the mean, median, or mode. Median or mode are just different ways of calculating the average. Meaning is what you know as the average, like sum all the values and divided by the number. Median is list all the values here and get the middle element. Let me just illustrate it. My computer is acting super slow today for some reason. Okay, so if you have something like 5 or 4 to 1, the average, the mean is going to be the sum of this. So 16 divided by 5 is going to be something like 3.2, right? If you want to calculate the mean, you're going to order it. The median, you're going to order it. It's already ordered, and pick the center here. And if you want to do the mode, you're going to get the element that's appearing the most often. That's 4, so that's mode, median, and mean. So this is your standard average as you calculated. This is the median element in the list, and this is the element that is appearing most often. In case you aren't familiar with the terms, why do you want to fill it with those values? For if you're doing machine learning, what machine learning models actually do is that they figure out the statistical description of these elements and their interconnections and so on. So entering the data that's the mean to the entire data set won't offset it significantly. It won't indicate an error, and entering something like a 0 is probably a bigger error. In the past, before machine learning, we usually did something that's called like a guardian value or something like that, which just indicated that is an error, but you can still process it, because if you have something like nan, not a number, you can't run any calculations in it. So we would just insert like a guardian value of that a numerical value that's impossible, like 10,000. But today you don't want that errors to happen, today, and to get the data actually fed into machine learning algorithm. Flagging is essentially just noting, hey, there is a missing value or an erroneous value in this row, and then someone will later check it on. You won't use that row in any analysis, and avoidance is simply using algorithms that can handle missing values. Imputation, as I mentioned, you can input like mean, median, or mode values, but you can also do it with some stuff like k-nearest numbers, based on the, if you have two values that are one next to another, you can one next to another, you can fill out the medium, the missing value in between them. You can use models like random forest to do iterative imputation. You can do matrix factorization, and there are a lot of techniques. I didn't mention Boltzmann machines here and so on that you can use to input data into the data set to make sure you are essentially trying to guess the value of the missing data based on the other data. What happens if you have noisy data? When we are talking about noisy data, we are talking about you're doing measurements and you get something like this. When in reality, you would want to get data that's like nice and smooth here, without any errors or any like these jumps in here introduced by noise. You can smooth the data. Moving average is a very common algorithm, polynomial smoothing and so on. It's a whole science in itself. Signal processing to get like smooth data is an entire field of science on its own. So there are a lot of techniques. Binning is basically grouping values into intervals. So you control that noise. You can do clipping. So you say like, any values outside of the range that I am expecting are going to be eliminated. We simply aren't going to use them. You can do something like a logarithmic transformation, so you control the data and stabilize it a bit, and you can, like as I mentioned, eliminate any outliers or anything like that that you may have issues with using standard statistical elements. Duplicate data, again, you want to figure out, you want to eliminate any duplicates, as I mentioned, because they can read information. You can introduce a bias into machine learning algorithm and cause a lot of elements. Again, when you have 100 data points, that's simple. When you have 100,000 data points, that's much harder. When you have millions or billions of data points, that's a significant problem. You can just compare everything one by one. So that comparing one by one, you just check every row, every value in each row and against all other rows and make sure it's the same. It's like that basic naive algorithm that you may have. So what are you going to do? You can do exact matching by calculating a hash or a checksum or something like that and see if there are any of that. That's great if you have a data set that has a ton of variables. So we're saving a lot of time by compressing those variables into one. Fuzzy matching is using a similarity metrics to see things that are similar. Other stuff is like near duplicates. For example, sometimes you want sometimes data that's not exactly duplicated, but is close to being duplicate can be treated as duplicate. This really depends on the analysis that you're doing. A lot of times, this isn't necessarily a problem, but it can be a problem in some cases. Or the data is just different in elements that aren't key to you. So so if you're like variables that you don't need differentials to data points, that's essentially duplicate data point for you. So you can what you can do is use fuzzy techniques to figure that out. And other duplication is just how are you going to do? Are you going to delete stuff? Are you going to if you have some near duplicates, are you going to merge them and preserve some values? If they are just double duplicates, are you going to delete them? If you think that the duplicates themselves may be significant, again, you aren't necessarily paying attention to, are you going to store information and say like, hey, this data point had a few hundred duplicates in the data and so on. Are you going to store that, or aren't you? Those are some elements that you need to consider. Again, I mentioned when it comes to consistency, when it comes to standardization, you want to make sure that units are uniform. Check that. This is especially a problem when you are have people manually inputting stuff, right? They will input in whatever is simplest, whatever they are used to. Same goes for data type validation. That's easy to check. If you try to sign up somewhere and it asks you to type in your phone number and you type in text, it's going to automatically tell you like, hey, you need to type in that's not valid or so on. Again, you need to have a standard to know what's going on, because it's fine to try to enforce your consistency or data type validation, but you need to have a standard that includes all possible use cases and so on. There is also the problem of scaling. That's something you possibly mentioned in machine learning, so I'm just going to quickly mention it here. But basically, when we're doing machine learning or some other analysis, scaling data to normal to certain range, like from 0 to 1 or from -1 to 1, can be very useful for training different algorithms because they are sensitive to scale. So you may want to do this as a part of your data cleaning process. And obviously, if you're doing it, you want to use some robust scaling techniques, because if you have a lot of outliers, they can damage your data. Another is, encoding data when you have categories. How are you going to encode them? We're talking about if you have something like type of the car. Do you want to do, and the car can be, a hatchback, a limousine, a caravan, a van. You have 5 or 6 different categories. One is one-hot encoding, where essentially you're going to take, if you have something like, hatchback as class 1, then you have, I don't know, limousine as class 2 and SUV as class 3. One-hot encoding, for example, for a hatchback is going to be something like in the first spot I'm going to have 1, then I'm going to have 0 and 0. That's called one-hot encoding, right? So a limousine would be stored like this, and SUV would be stored like this, right? That's one-hot encoding. We just use the spot of this one in this array to check, and this is pretty nice because you can easily validate it. You can just sum this. If it's different than 1, you have an error. Label encoding is essentially what we've done here, where we assigned 1, 2, or 3 to some textual values, so we can use it as a text. If we have like categories that are ordered in some way, maybe best, we have like best, average, worst. You want to assign values to them that make sense, so it's easier to figure out when you're analyzing without converting that back, because if you have something like if you have a situation where you have categories like good, best, good, average, okay, and bad, if you use, for example, like grading system, for example, in Croatia it's 5 for the best and 1 for the worst. You can use this, and without needing to, because you follow this order, when you're analyzing the data later on, you don't need to convert these categories. Obviously, we'll still write this down and document it, so you don't, if someone comes later on and isn't familiar with what you wanted to do, they can get it. But the benefit of this is that you automatically know, like, oh yes, whenever you see this number 5, you can associate it with the value without needing to change the data. And again, categories, target encoding is when instead of that you don't know what to name it. Maybe you have some random groups of numbers or something. So you're going to use to replace that. You're going to use that min target value as the name of that class. What you're going to choose obviously depends on your data and your data sets. There is again feature engineering for pre-processing, whether you want to create new features, right? Feature engineering refers to just taking any variables or columns in your table. If you're thinking of data as a table, if that's how you're visualizing it, features are are individual columns. Variables that you want to convert, whether they are text, you want to convert them into elements. You want to create new features, like for example, the simplest example is if you have a first and last name, you want to split that into first and last name, right? You want to calculate something, you want to combine something, and so on. Like if you have, for example, in my PhD, I had the position management, and I wanted to calculate the speed by taking the difference in position between two measurements, right? So that's something that's called feature engineering. You can do, automation in data cleaning. You can do, you can use, as I mentioned, ETL pipelines. There are frameworks that exist. I mentioned DQ. You also get expectations. You also have Apache Airflow as another. Scripting in Python or R is very popular for data cleaning and data processing. And again, I mentioned monitoring. You want to monitor stuff. You want to have someone who does either a human checking it or some automated system. Again, some things that you need to pay attention to here is you want to understand the context. Again, if you have weight, some variables called weight measurement. What's that weight measurement of? If it's a weight of the person and you get 5 kilograms, it's possibly an error unless babies were included, right? If you have a weight of a car and you get something like 70 tons, that's probably also an error, and so on. So you wanted to understand the context when you're analyzing the data. You want to document changes. So you can reuse stuff that you built, and you can adjust it later on. Any refinement is iterative. So once you fix something, build upon it. Don't necessarily go when you're programming, where you're trying to design a solution. Don't immediately go and try to deliver a complete solution. Iteratively refine it because there will be changes that you can't expect now, that aren't present in your data now, that will appear. That those are the things that you're going to change. That's something that I always tell the people if I'm building something like an automated cleaning program for you or something like that. You will want to probably hire me for maintenance in the future because I don't see the future and I can see the future. And usually, if someone promises you, that's something you need to be careful of. If you are not the developer yourself, something so like, oh, we will guarantee you, 100% that we will process all the data in the future as well. It won't be problems. They either don't know what they are talking about, or they are trying to get themselves out of like a maintenance contract or something like that. You want to validate all the data, and you want to make sure, again, when you're designing pipelines, you want to make sure that is scalable. So don't be like, oh, that takes 5 minutes on my computer. It's fine. No, what's going to take once you have 20 times the data that you have now? Is going to still be fast enough or not? Okay, and for the last topic, I have just like 10 slides discussing the future of big data and what the future of big data and some elements that are going to that are either emerging. This is mostly I'm discussing like stuff in that I've noticed in different academic journals and stuff like that maybe isn't being applied now widely, but in the future it will, and especially if you're a student, if you are getting into an area, into a field that's using big data, I think this is useful to you because these are the approaches that you may want to, that you will need to be familiar with in the future. So again, what is happening is generally we get more data today. Much larger volumes, is much faster to collect data, it's much easier to collect data. Something like, when people got smartphones, that was insane. We suddenly got more data. Now we are minimizing that. When it comes to healthcare data, we are getting a lot more like smart rings and devices like that you can just charge once in 2 weeks, pop on your finger, it's going to measure your body temperature and so on, your the oxygen levels, etc., and it's going to store it on a server, and you can use that for analysis in the future. And you're getting more and more of that sort of data sources today. AI-based, quantum computing-based softwares and so on are something that we're talking about using. We aren't still necessarily, yes, AI is being used, machine learning and so on. Quantum computing, not so much, but there are some techniques. And basically, what people are focusing on is make it simpler to make better decisions and provide stuff in real time, right? And allow it to scale further. So again, AI. Basically, I already mentioned this. I already talked about it. Is you have, AI is what big data and AI, are something that you mostly want to discuss together today because the amount of data is what enables AI application today at the level it is, and AI justifies the collection of data going forward. So it's kind of a beast that feeds upon itself. When you have like AI and big data, it's like a chicken and egg problem. You have both are important to each other. Uh, Again, especially what we're doing is predictive modeling in the industry today. We want to figure out, when the faults are going to happen, where the errors are going to happen, and so on. Any outliers that happen, any anomalies that we want to handle manually. Like in the simplest example is like if you are developing an online game and you have people who are acting differently. Maybe they are bad actors. You want to ban them from your service. Maybe they are the people who are investing a lot of time and a lot of money with that in the game. You want to reward them in some additional way, keep their interest and so on. So that's something that happens. What we are generally talking about is, deep learning models. Deep learning usually refers to, when we're talking about machine learning versus deep learning, we're talking about the size of the models. Deep learning models are bigger, deeper. If we are talking about like neural networks, they have more layers that we are using in them. And the second, you need less data to be, you aren't structuring the data so much. So for example, in machine learning, you will get images and you would process that images into numbers to feed them into the model. Today with deep learning, you're just going to feed it images directly or videos directly. Same with natural language processing. I talked about this, ChatGPT. There are a lot of cases for this is used. Reinforcement learning, you probably mentioned reinforcement learning in other classes, but it's just you can really easily build reinforcement learning algorithms upon big data, especially big data that is being fed, and you can retrain these algorithms again. And they're really easy to scale as you get more data. The benefit of AI models, like neural network and so on, is that they are very, very fast. Training them is slow. But once you have a model trained, it's very, very fast, it's very useful, and it's going to give you insights very, very quickly for various different insights. And here you probably, I don't know which tools you used in other classes that dealt with AI. You probably used scikit-learn, maybe you used TensorFlow, maybe used PyTorch if you work with Python. I also mentioned Apache, MLib for MLlib, for if for data that's already stored in Hadoop, and you want to use Apache Spark to process it. What are we going to do in the future? We're going to have something that's being worked on. It's AI-driven self-healing systems. What the self-healing means, it means that when we have an error in the model, it automatically corrects itself, right? So if we get a different data source and you have like you're collecting data from different countries, you add a different country, is going to automatically retrain itself to generalize better. It's going to detect an error, process a retraining algorithm, and feed it feed itself, upgrade itself as it goes. Again, the biggest problem with this is high storage requirements for AI models, and this is talking about models specifically, not the data. Today, we are talking about data centers that use so much water for water cooling that it's causing issues in ecological sense. That's how much compute power we're talking about. Again, there are ethical considerations with data. When it comes to integrating diverse data types, diverse data sources, it's very hard to do it. So it can lead to biases. We talked about this in social aspects of AI class. If you participated there, and again, most AI today, especially when it comes to deep learning, natural language processing, these are very, very complex models that are hard to explain. And when something's hard to explain, it's hard to gain trust in how this works. Then we have, quantum computing. I mentioned it. I'll say immediately, I'm not really a quantum computing expert. I know it exists. I know it uses qubits instead of bits. It uses certain quantum properties. I want to talk at length about it here. Again, I'm not really an expert in that area, but I know that it enables to do certain types of analysis, especially distributed analysis, very, very, very fast, and that certain algorithms that were out of reach for us before because they were too slow to apply on large amounts of data can be used with quantum computing. So here are some algorithms, just to note. Grover's algorithm for data search, quantum approximation optimization, for when you want to run optimization in a large data set, it can do it practically automatically. Machine learning adjusted to quantum systems. So that's something that in the future, as building quantum computers grows simpler and cooling them gets simpler, the technology develops. You may in the future have quantum computing setups to be much more common. Again, whether you want to run it in anyways where you want to generally analyze big data, you may be able to use quantum computing instead. That's how simple it is. The problem is that this quantum computing infrastructure systems are still being developed. You aren't at a point where you can buy a quantum computer and mount it even in a data center or something. You need you need to specifically build it, right? It's very expensive, and there aren't a lot of people who understand quantum computing and who are experts in quantum computing. And there are even less people who are skilled professional in both quantum computing and big data who can integrate it together. It will come with time probably, but for now it's not there yet. And just in the future, what are the growing applications that happen? You have healthcare, you have finance, retail, and transportation. Transportation is very interesting because, especially in big cities, in healthcare, we talked about that. It's in use even today. Big data is a lot in use in finance. It's very commonly used. Same goes for retail and sales. Transportation is a relatively new area where figuring out stuff like what is the optimal way to turn like traffic lights on or off, or to for example, reroute certain roads that are designed to be rerouted, uh, and so on. These are the kind of the things that, as our cities grow and as our transportation gets more complex in a city, is something that we need to is something that's going to be used a lot because people aren't planning on giving up cars anytime yet. Of course, we are also focusing on ethical concerns much more than like 15 or 20 years ago. People are much more data conscious. People don't want their data shared and used without, additional knowledge. So that's something that's, additional regulations will happen and are happening as we speak right now to regulate data more. One of the biggest problems, I mentioned quantum computing, so I'm going to mention it here, is that current like encryption protocols and stuff we have that protects our data isn't. Those algorithms can be easily broken by quantum computing, some of them. So that's something that we need to look forward and adjust like rules and regulations that dictate usage of those algorithms. We need to adjust them in a way that allows for that uses algorithms that are robust against this. Again, AI combined with quantum computing and additional, more advanced analytics methods that are being developed will improve big data. It will be a separate new era or continuous growth. Again, big data. People have been collecting data ever since 90s without machine learning and AI being mentioned. When AI emerged, a lot of people started collecting more data, started panicking, started wanting to collect data more. But that was like a new era, definitely, when people started using AI. Additionally, so will quantum computing be the next era like that in big data? It's possible. We'll see what the future brings. What will definitely bring is further emphasis on scalability and ethical data collection and so on. That's something that today you can't apply for funding, or you can't try to start up a project without focusing on ethical aspects and so on for a good reason. But essentially, what the future will definitely is focused on. We want to have a full automation big data. We want to have from the point that it is generated, we want to automatically input it, automatically reprocess it, automatically feed it into a schema, automatically analyze it, and put the result that we are interested in outside. We don't want to provide any additional inputs. That's the goal. That's what we want in the future. We want that full automation, self-optimization, where the algorithms are adjusting themselves to the current needs and are being fed. So whenever some data is generated somewhere, we are automatically in essentially real time, essentially as it happens, getting predictions, getting measurements, and getting information, so we can decide on how to adjust our operations in the future. And that with that, we end this class. Thank you very much for your attention for these past 2 weeks and before in other classes. So I believe that I hope that you will learn something useful here, and yeah, that's essentially it. Just in case this is your last class that you have, you will by the end of the week receive information about certificates, and there will be another form for you to fill out, so we can like issue the certificates to you, and so on. So you will get that in an email. So don't worry. And that's it. Thank you very much for listening to me ramble on about big data for like 10 hours. And I wish you, good fun in the other classes and so on. Thank you and goodbye.
Thank you for the lessons. Goodbye.
Bye.
Thank you. Goodbye.
Thank you.